Okay, last video on thermochemical equations, we're going to look at two different ways that we can find the heat of a reaction using thermochemical equations. Okay, so the first one is using what's called Hess's law. And Hess's law states that if you can add two or more thermochemical equations to produce a final equation, then you can sum their enthalpy changes to find the final enthalpy change. So we're going to work through this problem and show you exactly what Hess's law is all about. So it says use the thermochemical equations A and B below to determine the delta H for the decomposition of hydrogen peroxide. So what we're going to look at here is here's the formula that we want to get, okay, and we're trying to find the delta H for that reaction. And we have these other two reactions we can work with that we know the delta H of. So what we're going to do is we're going to try and find a way to add together A and B so that it equals this equation right here, okay? Now, what we want to do is two things. One, we can reverse a reaction, and if we reverse a reaction, that's going to change the sign of the delta H, or we can multiply through and change all the coefficients, and if we multiply, we're going to multiply the delta H as well, okay? So if we take a look at equation B, we can see that hydrogen peroxide is on the reactant or on the product side, but we want it on the reactant side. So equation B, we're going to have to reverse. So we're going to write equation B, H2O2 yields H2 plus O2, and that's going to change its delta H from negative 188 to positive 188 kilojoules. Okay, now we have H2O2 in the reactants like we want, but we only have one here and we want two. So we're going to go through and multiply this whole reaction times 2, which is going to multiply our delta H times 2. Okay, so now that looks good. If we look at equation A, we have 2 waters in the product. We want 2 waters in the product. So we can leave equation A like it is, and we're going to rewrite it. 2H2 plus O2 yields 2H2O. We're going to leave the delta H because we didn't change the reaction, and keep it negative 572 kilojoules. Okay, so now if we add these two reactions together, okay, if there are things that are the same on both sides of the arrow, like the H2s, we can cancel those out. And then here we can cancel out this O2 and cancel one of those, okay? So we have the things left that we want in our final reaction. So when we put it all together, we get 2H2O2 yields, in our product side, we have O2 plus 2H2O. And that's what our final reaction looks like. So we were able to add these two together to get this, which means we add our kilojoules together as well. So if we multiply 188 times 2 and then add it to negative 572, the delta H for the decomposition of hydrogen peroxide comes out to be negative 196 kilojoules. And that was what we were trying to find, the delta H for this decomposition reaction. So there you go. That's what Hess's law looks like. Okay, the last and final way to find the heat of a reaction is to use the standard heat of formation. And the standard heat of formation is basically how much heat it takes to form 1 mole of a compound from its elements in their standard states, okay? So because elements are already made, we don't have to make them. Their heat of formation, and you're going to see a little F right here, that stands for formation. For elements, the heat of formation is 0. For compounds, there is an entire table of heats of formation. It's on page 975 in your textbook, or you can see I have the same thing right here. So if you take a look, for example, the first one is solid silver. Its heat of formation is 0 because it's an element. But all right, if we take a look at a compound, for example, CH4 gas, that's going to be its heat of formation. Okay, so we're going to be using this table to figure out the heat for a chemical reaction. So to do that, we have an equation to use. To find the heat of a reaction, we're going to take, and this little symbol right here is sigma. It means sum of. So we're going to add up all the heats of formation of the products, and we're going to subtract all the heats of formation for the reactants. Okay, so we're going to go back to that table and look at that. All right, so let's take a look at our example. Use standard heats of formation to calculate the delta H of reaction for the combustion of methane. Okay, so the first thing we need to do is write our balanced equation so we know what the reactants and the products are. So when we talk about combustion, if you remember, combustion is something plus O2. Methane in this case is CH4 gas, and we need to know the state because that is going to help us figure out the heat of formation. Plus oxygen gas yields carbon dioxide gas and water vapor. Okay, so we need to balance our equation. So we need 4 hydrogens. We'll put a 2 right there. That gives us 2 plus 2 is 4 oxygens. So we'll put a 2 right there. There's our balanced equation. Okay, so keep that balanced equation written down. We're going to go back and look at our heats of formation table and see if we can figure out all of these heats of formation and then use our heat of reaction formula to calculate that. Okay, so here's our heat of formation table. So we are going to calculate our heat of reaction by first looking at all of the all of the products. So if we look at our products, we have 1 mole of CO2 gas. And if you'll notice, the delta HF is in kilojoules per mole. So we're going to have to multiply by how many moles are in the balanced equation. And for CO2 gas, it's 1. So let's come down here, our list. CO2 gas is right here. Okay. So for our our products, we're going to have 1 mole times negative 393.5, and that's for carbon dioxide. And then we're going to add 2 moles times H2O gas. So let's come over here, look at our H's. We have H2O liquid, H2O gas. That's the one we want right there. So negative 241.8. Okay, so there are our products. Now we're going to subtract our reactants. Okay, so in our reactants, we have 1 mole of CH4. So let's find CH4 gas. There it is right there. So 1 mole of CH4, negative 74.6, plus 2 moles of oxygen gas. So we'll come over here to the O's. LMNO. Here's oxygen gas, and it's 0 because it's an element, right? So anytime you have an element, it's going to be 0. So when we do all of that math, what you're going to see is our total heat of reaction. Scooch this over. The total heat of reaction is negative 802.5 kilojoules. There you go. Okay, and it is negative. Combustion reactions are exothermic, so that makes sense. So you've seen lots of different ways of coming up with heats of reaction for thermochemical equations. We're going to practice all of these in class, and you'll definitely need this chart, so we'll have to look it up in the book when we use it, and you'll be given the chart on the test.